In this session, we will be exploring the replication and sharding in MongoDB. Few words about me. I am working as a database consultant with Python. I joined Python in 2014 in the open source database practice, and since mid of 2016, I am working as a lead database consultant for MySQL and MongoDB practice. From 2015, I am a MongoDB certified DBA, the 300 DBA certification. In this session, we will be speaking about what is a replica set in Mongo database, how the replication works, what are the replication concepts. Later we will see about the replica set features and the deployment architectures. We will speak about vertical versus horizontal scaling. Then we'll continue to a sharded cluster in MongoDB. What are the components of a sharded cluster? We will see about the different shard keys that we can define in a sharded cluster, what chunks represent, and at the end we will discuss about hashed versus ranged based sharding. You can ask questions anytime. You can interrupt me. So replication in MongoDB is maintaining the same data set from multiple processes. That's the basic definition of replication in any database. Primarily, we do want to maintain multiple copies of our database because we want to provide high availability by maintaining multiple copies. The replication provides high availability, but it does not scale. So the replication itself is not a scaling solution. It's primarily for high availability, and by some points it can increase our read capacity because moving from a single node, we now have multiple copies of our data where we can read from. With MongoDB, the replication goes in the following way. There is client application that speaks to the driver that is connected to the replica set. Initially, all the write operations go to the primary node. The primary node stores all the changes to the data into a collection called operations log. And once the changes are recorded into the operations log, then asynchronously all of the entries in the operations log are replicated to the secondary nodes in the replica set. Once the changes are replicated to the secondary members in the replica set, both or all of the secondary members in the replica set will copy the op log into its own operations log. So by doing that, it's allowed the secondary node to use sync source another secondary. And that's by default in every replica set configuration. The setting chaining allowed is true by default, and once the secondary sees that there is another node that is not lagging more than 30 seconds, it can initiate the sync source to another secondary. You can disable this setting if you want to always replicate from the primary node. One important setting for the replica set members in MongoDB is the operations log, and the operations log itself is a kept collection that keeps a rolling record of all the operations that modify the data in the databases. It's idempotent. It means that you can replay all of the operations in the op log as many times as you want. At the end, it will have the same result. It's important to mention the default op log size for Unix and Windows systems. By default, it will take 5% of the free disk space. So if you are starting a replica set with small disk size, probably the op log collection will have small size, and that will be important for your replica set if later you have many write operations that will modify your data, or even high amount of insert records. The operations log is the log that maintains how long your replication window will be. Initially, for deploying a replica set, if we come from the MySQL world, we may think there are two nodes for maintaining a replica set, but that's not the case with MongoDB. We should always start with at least 3 nodes and form a replica set, because by having 3 nodes, we can have majority for election when there will be 1 node down. Starting a replica set is you can install the binaries from any package, or even from tarballs, unpack on the 3 nodes. It's worth mentioning that all of the 3 nodes should be able to speak to each other in the same network, whether it will be local network or one network. So once we have the binaries installed on all of the nodes, we run rs initialize on the first node, and once we do that, we have the primary node for our replica set. Now it's interesting that we already have a replica set, but it only has 1 node. Once we do that, it's very easy to set up a replica set in MongoDB, because what our next step is to add the rest of the nodes, and we are doing that by just running the command rs add and specifying the host name and the port that the host is listening to. Again, everything in a replica set is maintained from the primary node. We run rs add on the primary node, and it already knows what the secondaries are, and from the same time, the secondaries will start copying the data from the primary node. Each replica set can have up to 50 members, and 7 members can only vote in elections. There are different configuration options. We can have arbiter node, we can have priority 0 node, hidden nodes, delayed node. We can manipulate with the write concern, and the read preference for the replica set. The arbiter node is only part of the replica set, and it votes in elections. It does not hold copy of the data. And this is mainly used when we need extra copy of our data. We can have primary and secondary. We don't want third copy of our data, but we need a third node that will be voting in the elections. So that's why arbiters are used. Or we can use arbiter if we have deployment in 2 data centers. Each data center have 2 data nodes. And now, if one of these data centers goes down, we need an arbiter node that will participate in elections, and one of the other data centers will elect primary node. Priority 0 node is member from the replica set that never becomes primary. If we set the priority to 0 to any member in the replica set, then we should expect that the node will never become primary, and however, it will participate in elections and it has votes. So this is useful with the same example as the arbiter node. We can have 3 data centers, but in one data center we don't want any node ever to become a primary, and we do that by specifying the priority to 0. Similar to priority 0 node, there is option to set hidden node, but this is a little different. While priority 0 node will be visible to the driver and the applications can direct traffic to the priority 0 node, hidden nodes are not visible to the driver, and by that our application cannot see the copy of the data. So we should be cautious while setting hidden nodes. Hidden nodes can also will never become primary node because the priority of the hidden node is 0. Mainly the use cases for hidden nodes is we set hidden node that the application will not see, but we can query manually by doing reporting or backup jobs on those nodes. Delayed node is a node where we can set the replication thread to delay from the primary node by a certain amount of seconds. The delayed node must be a priority 0 node, so it does not get elected as a primary node. This is important in elections because as the node is delayed, we don't have the latest copy of the data, and we don't want this node to be elected as a primary whenever there is a failover in the replica set. However, this node will participate in elections and it has votes. So again, with like the hidden node, this node can serve reporting jobs, or it's primarily used for backups. One consideration for delayed node is that we should monitor the oplog size and how long our replication window is, so that we don't override the oplog and make the delayed node out of oplog entries. It depends, not very common, but from delayed node, if you run some delete operation on the primary, you have at least maybe hour or two to get that data back from the delayed node. So that's why they're useful. One important setting for replica set is the write concern. This setting is mainly managed from the driver, and it allows the application to have a response from the replica set on how many members the write succeeded. By default, this is only one member from the replica set, the primary node, but we can change it. We can have W two members, which means that when we do writes on our replica set, we are expecting at least two nodes from the replica set to acknowledge the write. However, this may not work as expected, because even if we have write concern of 2, which means that we can expect 2 nodes to acknowledge the write, or the write will fail. With MongoDB, if we have a timeout on a write concern with 2, that does not provide a guarantee that the write did not succeed. So the write may be successful on the primary node, but we did not get acknowledgement from another member that the write was successful. So the option is only to have acknowledgement from as many nodes as we expect to acknowledge the write. However, the writes may be successful on the primary, and it will get replicated. So we should expect that this behavior is possible with MongoDB. Another setting for a replica set is the read preference. This shows how the read operations are routed to the replica set members. By default, the driver will send all the read operations to the primary node. But sometimes that's not what we always want. We can change this property, and we can make the setting primary preferred. With primary preferred, by default, all of the reads will be sent to the primary node, but in case the primary is not accessible, the driver will route the reads to the secondary nodes. The other setting is if we set secondary as a read preference, and by setting secondary as a read preference, the driver will always send the reads to the secondary nodes. Similar to the primary preferred, we have option to set secondary preferred, and by that, the driver will always try to send the read operations to the secondary, but in case the secondary is not accessible, it will route the read operations to the primary. And there is another option for setting nearest in the read preference, and with nearest, the read can go to any node depending on the latency between the driver and the nodes. So the driver sends ping to all of the nodes, and based on the network latency, it decides what's the nearest member, and then it can send the read operation to the nearest member. Starting from MongoDB 3.4, there is max tailness seconds property, which allows us to set read preference to secondary, but only if the secondary is no longer than certain amount of seconds lagging behind the primary. If it's lagging more than 300 seconds, for example, don't read from the secondary, go to the primary.
How does it know if you pick up secondary? Which secondary is
it does not. So it routes by round robin, yeah. So the replica set allows us high availability, but at some point of time we want to scale, and we have our data set, the working set grows. One thing that we can do is scale vertically. We can add more CPU, we can add more RAM, even we can increase the disk size or have faster disks. But at some point of time, we're limited. We cannot scale our hardware indefinitely. So what MongoDB allows is horizontal scaling or sharding, and primarily the horizontal scaling is not something that MongoDB invented, but this is a method for distributing our data across multiple machines and having our data spread across multiple horizontal partitions. How this fits into MongoDB? Everything that we already discussed about replica set is turned into a shard or a partition. And with MongoDB, we have router and config servers. So each component is part of the sharded cluster, and it's important for the MongoDB clustering. As mentioned previously, the shard or the partition should be a replica set, and that's important because we want to keep multiple copies of our data in a single partition. The other important part of the sharded cluster are the config servers, and that's where the metadata is stored for the sharded cluster. The third part is the router or the mongos. That's the interface for our cluster, and all of the operations that go from the application to the sharded cluster should go through the mongos. We shouldn't do any changes to our data directly going to the shards. However, we have that option, but we should definitely know what we are trying to do by modifying the data directly on the shard. Everything in a sharded cluster should go only from the routers or from the mongos. Once we have our replica set, the deployment to the sharded cluster is having the config servers and having our mongos. The shards itself are added through the mongos interface simply by running the command sh add shard and the shard name. Once we have initially a sharded cluster with one shard, then we can add as many shards as we want. So the shard or a replica set in MongoDB cluster is a subset of the data, and it should be used as a replica set to provide high availability. Every cluster has primary shard for each database. When we create a database in a sharded cluster, the database initially is stored on one of the shards. So we may have 5 shards, but initially when we create the database, it will be stored on shard 1. So that's the primary shard where the database resides. It's important to mention that all the collections that are not sharded will reside on the primary shard. And this is important because after some time, we may be experiencing high load only on a single shard from our cluster, and we may be wondering why that's the case. But all the non-sharded collections in the database will reside on the primary shard for that database. So starting from MongoDB 3.4, all the shard members in a sharded cluster must have the option shard server in the configuration file and must be running, by default, will be running on port 27018. So the question is it possible to have more than one sharded collection? Yes. We can have as many sharded collections as we want. Each collection is sharded separately. We'll get to the sharding in a few slides. The other important part of the sharded cluster is the config servers. The config servers are storing the metadata for the cluster, and that's where the information for each document in the database on what shard is located resides. Other than the metadata for a sharded cluster, the config servers also store the authentication configuration, and that's stored in separate database called admin database. One important change starting from MongoDB 3.4 is that the balancer that is balancing the chunks in a sharded cluster now resides on the config server primary node, and the config servers by default will run on port 27019. The last part of the sharded cluster are the MongoS nodes. The MongoS nodes are the interface in the sharded cluster, and they don't have any persistent state. The MongoS updates the state whenever there are changes in the cluster metadata. And before MongoDB 3.2, the MongoS also had the balancer, which is responsible for balancing the data between the shards in the sharded cluster. All the operations that go from the application to the sharded cluster must go through a MongoS, because only the MongoS has the information what document on what shard can be found and in what chunk. So we have our sharded cluster deployed and ready, and we have our database, we have our collections. Now the next step is to actually shard our collection and shard our data. First, for sharding a collection is enabling sharding on a database level, and we do that by just running the command sh.enable sharding, and we specify the database name. Once the sharding is enabled on a database level, the next step is to shard the collection, and there are two ways for sharding the collection. We can shard on a range-based sharding, or we can shard on a hashed-based sharding. But before we move to sharding, maybe the most important step that we must do in a sharded cluster environment is to choose our shard key. The shard key should have all of these properties so that we can be certain that our data will be distributed evenly across all of the shards, that we will not have hot shard, and we will not have huge chunks that later will be that later the balancer will not be able to move across the shards. So the first option for a shard key is the shard key should have large cardinality. That means we should have enough unique values for the shard key so that there will be many splits from minimum to the maximum value in the shard key, and that we will have enough chunks that later on will be balanced across the shards. Sorry?
If we have a unique distributed, is it a good candidate?
So the question is, if we have a unique key, is that a good candidate? Yes, that's excellent candidate. So, for example, if we have user ID and the user IDs are unique in our collection, then probably that key is quite a good candidate. The other option for good shard key is that it should have low key frequency. What that means is, even if the shard key has high cardinality and many unique values, maybe there will be some key that has too many values in our collection. So with the example of a user ID in the user's collection, maybe some users have, most of the users will have hundreds of documents in the collection, but some users might have hundreds of thousands of documents in the collection. And if that is the case, probably we should think about compound shard key and not only the single shard key. And the other important setting for a shard key is that it does not have a monotonically increasing value like timestamp or object ID. But this property is more for range-based sharding, while it will work good if we are doing hash-based sharding. Once we define our shard key and we shard our collection, the documents are logically grouped in chunks. There is no physical division of our data in the cluster, but all of our data is logically grouped into chunks. And the chunk is simply a continuous range of shard key values that reside on a particular shard. It has the lower bound of the shard key inclusive and the upper value of the shard key is exclusive. So, for example, if we have a shard key on some number starting from 20 to 30, 20, the value of 20 will be in the chunk, but the value of 30 will not be in the chunk, and so on up to the max value. The default value of chunk in a sharded cluster is 64 megabytes, which means that once the chunk size gets approximately to 64 megabytes, there will be a split, and the split allows the next chunks that will be formed from this splitting to grow up to 64 megabytes and so on. So the cardinality of the key is important because if we have few unique values for our shard key, then we are limited to have multiple chunks in our system. And for example, if we have only 10 unique values for our shard key, then in our system there will be maximum 10 chunks. And those 10 chunks can reside each chunk on a separate shard, but we are limited with 10 shards only. Our cluster, even if we have 20 shards, we are limited with distributing the data across those 20 shards because our cluster cannot split our data in more than 10 chunks. So that's why it's important to have a good shard key cardinality. However, the chunk size by default of 64 megabytes can be changed, even if we want to change to a lower value or if we want to increase the value. So the first option for sharding is range-based sharding. That's dividing our data into continuous ranging that are determined by the shard key values. So what that means is if we have numbers from 0 to 100, the sharding will be distributed from the min key up to the max key, and probably the documents that have closer values like 25 and 26 will be probably reside on the same shard. So this is important when we do find operations in our sharded cluster, because if we want to scan and find the documents where the value is greater than 25 and less than 30, probably this operation will be run against a single shard, and we will not have to query each shard individually and then merge the result set. So the range-based sharding will work if we want to make sure our find operations will always get their result set from a single shard, or we should be aiming to get the result set from a single shard. So,
Just a kind of mixing the words shard and chunks. Is there any difference that we should think about?
So the question is the difference between chunks and shard. Shard is a section of the cluster that has horizontal copies of the data. So if you look at the shard in a cluster and have the shard itself has copy of the data from the cluster that is distributed. While in the shard itself, the data that resides in the shard itself is split into multiple chunks. Okay? Opposite from the range-based sharding, we have option to shard our collection with hash-based sharding, and we do that by running a command to shard the collection with hashed key. It's important to mention that we do not need to compute the hash from our application. We just say use hash-based sharding for this collection on the user ID, and the MongoDB database will calculate the hash key for us and will store the data into appropriate chunk. We don't need to have some key in our document that is already hashed, and then to store that key in the collection. In this case, keys like object ID or timestamps that monotonically increase are good candidates for hashed key. But we should be aware that with hash-based sharding, probably the find operations that we run will have to be sent to multiple shards to find our documents. And that's mostly for range-based queries, where we search, for example, give me the documents where the user ID is greater than 25 and less than 30. Probably in that case, our query will be run against multiple shards, unlike the case when we have range-based sharding. Some of the shard key limitations are that it must be ascending index key or at least compound key that exists in any document in the collection. If we have single document in the collection that does not have the shard key, then we cannot shard that collection by using that key. The shard key cannot be a multiple index, cannot be text index, or geospatial index. Also, it cannot exceed 512 bytes. Like we already mentioned, or we didn't, the shard key is immutable. So once we set the shard key for a collection and we have a document with the shard key, we cannot update the document and change some value of the shard key. We can only delete the document and insert the document with new shard key. And also, the shard key is hard to change. It's not impossible, but it's hard because we need to have a logical dump, logical backup of our collection, then drop the collection, insert the data, and shard on new shard key.
Because it's going to redistribute everything back again on each of the shards based on the new one?
Yes.
At this point, with 3.4, there is not an option about changing the shard key and run some sort of rebalance so you can rebalance the whole thing. That's not a procedure.
No, at this time there is no option for changing the shard key just by running a command collection.shardKey change or something like that. Maybe there will be in the future, but at this time it's not. And that's why it's important to choose a good shard key for our collection at the beginning.
In that way, for changing, you have to dump each of the charts, do the change, and reinput everything back again.
We have to dump from MongoDB.
Oh, from MongoDB, you dump.
Yes, because we want to dump all of the shards. Maybe there are 10, maybe there are 20 shards. We have to dump everything, and that requires downtime. One other limitation for the shard keys is that if we have a sharded collection, we cannot add unique index on any other key. Only the shard key can be unique index in the collection. So to have a summary for the sharded clusters and the replication in MongoDB, we should always use a replica set with odd number of voting members, and that's important because if we have even number of members and half of the members fail, then we will not have a majority to elect a new primary. For dedicated functions like backups or reporting, we can use hidden or delayed members in a replica set configuration. If our dataset fits into single server, probably it's best idea if we keep the environment unsharded, unless our dataset grows and that we can no longer handle the data size in a single replica set. then we should start thinking of sharding. But the sharding itself adds complexity, and it's more difficult to manage than having a replica set and running our data in a replica set. However, if we decide to shard, we should always have our shards as a replica set. And that's important because each shard as a component in a sharded cluster must have high availability. The shard keys are immutable, and the max size of the shard key is 512 bytes, so we can now shard a collection on any key that is longer than 512 bytes. The shard keys must exist in every document in our collection. And if we choose range-based sharding, our data may not be distributed evenly across all of the shards. But if we choose a hashed-based sharding, our data will be distributed randomly. And this is important because when we do a query, we may have to run our query across multiple shards instead of just pointing our query to a single shard. Thank you. Any questions? Compound sharding key is sharding our collection on multiple keys. So for example, if we have collection users and we want to shard on user ID, the compound key will be shard on user ID and created at, for example, if we have some date. And we should probably do that if we have, if most of our queries are running like select, find user ID were created at greater than or less than, or we should aim to create our shard key based off what our query patterns look like. If all of the query patterns that we have in our application start with the shard key, probably that's the best shard key that we can find, the ideal shard key. Sorry? So the question is, do the shard key have to be indexed? Yes. The shard key itself must be indexed, or it must be the leftmost part of an index. We can shard, for example, on user ID created at, but the index itself can be user ID created at, status, and some other keys. Yes.
You spoke about how the unique part is important for the chart. That's the only one that can be unique on the collection that you're charting. There is a setting that you're creating that you can make the chart either unique or not unique when you're creating. Does that have any changes on the other fields as unique, or that doesn't change it?
Initially, when we have the collection and it's not sharded, we know that our key is unique or it's not unique. And if we know that our key is unique and we want to shard the collection on that key, we can. Later, when we shard the collection, we cannot add any more unique keys in the collection. And even if the shard key is not unique and we decide to shard the collection, later on we cannot add unique index again. We're running out of time. Any other questions? Or you can meet me in the booth. We have a Python booth. Just drop by and we can discuss more. Thank you.